So far, we have seen different algebraic operations on complex numbers. So for example, addition, multiplication, etc. Now we also know that a complex number can be represented by a point in complex plane. So in other words, when we say that we are adding two complex numbers, it means that we are adding 2 points in the plane. So what is the addition of these 2 points, and similarly other algebraic operations in plane? So this is going to be the part of our next discussion. So to understand this point, we can associate a complex number in plane with a vector. Okay, so given this complex number z, which is equal to xy, we can associate a vector to this complex number. So what is that vector? So that vector always has tail the origin, and the head of that vector is this complex number z. Now we have associated a complex number with a vector in plane. Now on one hand, we can add two complex numbers. On the other hand, we also know that two vectors can be added. Now what is the relationship between the addition of complex numbers and the addition of two vectors? Now recall that we can add two complex numbers in the following way. Now it turns out that addition of complex numbers and addition of associated vectors is the same. Now let's see how this is possible. Consider this complex number z1 with coordinates x1, y1, and consider another complex number z2 with coordinates x2, y2. Now as we have seen that we can associate two vectors to these two complex numbers, so this one and this one. So what is the addition of these two vectors? Now we know from vector analysis that two vectors can be added using parallelogram law. So what is parallelogram law? So these two vectors form a parallelogram, and the addition of these two vectors is going to be the diagonal of that parallelogram. So what is the parallelogram formed by these two vectors? So we shift this vector z2 to this point. So this is basically copy of z2, and similarly this vector corresponding to z1 can be translated in the following way. So this is once again copy of z1. Now this is the parallelogram formed by these two vectors. Now the addition of these two vectors is basically the diagonal of this parallelogram. So this is z1 plus z2. Now we also know that if z1 is x1, y1 and z2 is x2, y2, then z1 plus z2 as complex numbers, they have the following answer: x1 plus x2, y1 plus y2. Now is this diagonal, which is the addition of the associated vectors corresponding to z1 and z2, is this diagonal the same as this addition of complex numbers z1 plus z2? So for this, let's consider what are the coordinates of this point. Now if we focus on the coordinates of this point z2, then this is in fact x2, and this length is in fact y2. And when I translate this vector corresponding to z1, then since the x coordinate of z1 is x1, so this distance becomes x1. Okay? So which is exactly the same as this distance, okay? Because we have just translated this vector such that the initial point becomes this z2 instead of origin. So obviously the x coordinate remains the same, which is x1. From this point to this point, the distance is x1. And similarly, we know that this distance is y1. So when I translate this vector associated to z1 to the point z2, then this distance becomes y1. So in fact, this length is now y1 plus y2, since this length is y2. Okay? So we can say that this point has coordinates x1 plus x2, since this is the length x1 plus x2, x1 plus x2, and this length is y1 plus y2. So the y coordinate of this point is y1 plus y2. So since this is the addition of these two vectors, and this is also the addition of these two complex numbers. Okay, so this point has coordinates which is the addition of these two complex numbers. So we can say that addition of two complex numbers and addition of vectors are analogous, they are same. So similarly, we can subtract two complex numbers. So instead of saying we are subtracting two complex numbers, we can say that we are adding z1 and minus z2. So if I have this vector z2 and if I have this vector z1, then minus z2 is going to be this vector in the opposite side. Okay, so since if z2 has coordinates x2, y2, then this point has coordinates minus x2, minus y2. So we can translate this vector associated to minus z2 such that it is this vector. And this is going to be the addition of z1 and minus z2, or we can say that the subtraction of z1 and z2. We also know that we can multiply two complex numbers. We also know that a complex numbers is now associated to a vector in the plane as well. So from vector analysis, we know that we can multiply two vectors by using dot product, also known as scalar product, or by using cross product, also known as vector product. So these two multiplications, that is dot product and cross product, are different from the multiplication of the complex numbers. Okay? Or we can say that the multiplication of vectors coming from the multiplication of complex numbers. Now, our next definition is modulus of a complex numbers. So using this vector representation of a complex number, we can define the modulus or absolute value of a complex number. And this definition should be such that when we restrict this definition to the real numbers, then it should be the absolute value of a real number, since set of real numbers is a subset of complex numbers. Now once again, we use this vector representation of a complex number. So if I have this complex number z, which is equal to xy, then we have following associated vector with tail, origin, and head of this vector is xy. Now geometrically we say that the modulus of a complex number is the length of this vector. And how to calculate the length of this vector? So the length of this vector is basically the distance between 0, 0 and xy. So how to calculate the distance between 2 points? We know that if I have 2 points x1, y1 and x2, y2, these are 2 points in the plane, then we can use distance formula to calculate the distance between x1, y1 and x2, y2. So what is the distance formula? So the distance formula says that the distance between them is x1 minus x2 square plus y1 minus y2 square root. So in this case, first point is 0, 0, the second point is xy. So we can say that this distance from 0, 0 to xy, or the length of this vector, is in fact x minus 0 square plus y minus 0 square, which is equal to square root of x square plus y square. So we can say that the modulus or absolute value of a complex number is defined as square root of x square plus y square. Now if I restrict this to set of real numbers, so for example, if x plus iota y, okay, so is real if and only if z is equal to x plus iota 0. So this is a simple criteria to find the real numbers in the complex plane. So the criteria is this is real if and only if z is equal to x. So using this definition, we can say that the mod of x, if z is equal to x plus iota y, iota 0, mod of x is square root of x square, which is the same as mod of x. It's the same definition of absolute value from set of real numbers. Now, as an example, we can calculate the absolute value in the following way. If I have z is equal to 2 plus iota 3, then the mod of z is equal to square root of 2 square plus 3 square, which is equal to square root of 13. And from the geometry of complex numbers, we can easily observe that a number with mod 0 is exactly the origin. Okay, so origin is the only number with mod 0. Now, if I have two complex numbers with coordinates x1, y1 and coordinates x2, y2, then it's very difficult, kind of impossible to answer which one of these complex numbers is bigger than the other. Okay? So just like real numbers, if I have a number 3 and 4, then we can easily say that 3 is less than 4. And similarly, if I have any two real numbers, we can compare them. But in complex numbers in general, there is no such rule. But on the other hand, we can compare the modulus of these two complex numbers. So we can calculate the modulus of z1, which is a real number, and modulus of z2, which is a real number, and we can easily compare them. So what we have seen so far, there is a geometrical interpretation of complex numbers. We can associate complex numbers with vectors, and the algebraic operation of addition is the same as the vector addition. And we have also defined the modulus of a complex number.